Well, we have seen about the Gauss-Markov model and the Gauss-Markov theorem. I also mentioned that it was the theorem that we have seen so far is just a simple version of the Gauss-Markov theorem. Let's quickly recall what that was. In that theorem, we have this thing. We have the Gauss-Markov setup. We assume that x prime x is a non-singular matrix, and then we took any C and we said that C prime beta hat happens to be blue, the blue of C prime beta. I also mentioned that this non-singularity of x transpose x, which by the way is equivalent to all the columns of x being independent, that is x being full column rank, that condition may be dropped. So the general version of Gauss-Markov model is going to be something like this. We will still work with the Gauss-Markov setup, but we shall not assume that x prime x is non-singular. As a result, we have to sacrifice something. We now cannot work with any C. We need some condition on C under which the same conclusion will work. Now let's try to understand what that extra condition is going to be. The condition is already given in the book, but let's try to understand intuitively what that condition should be. So let's take this example. In this example, I have given you a simple linear model. So the first line is y1 is the beta 1 plus beta 2 plus beta 3 plus epsilon 1. The second one is also same, except that the error has changed, and in this way you have the first 5 lines all having beta 1 plus beta 2 plus beta 3. So we are measuring something which is beta 1 plus beta 2 plus beta 3 and with some errors. The remaining lines from line 6 to line 9, 4 lines, all have beta 1 plus beta 2 plus twice beta 3. Okay? And I assume Gauss-Markov setup, epsilon i's are all mean 0, uncorrelated, homoscedastic, etc. Now I ask you this question: how are you going to estimate beta 1 and beta 3? Just think in common sense way, no least square or anything, and you can guess very easily, sort of feel very easily, that beta 1 you cannot estimate from this setup. Why? Because beta 1 is always bundled with beta 2. Wherever beta 1 occurs, it occurs as beta 1 plus beta 2. So you do not have any hope of extricating beta 1 separately. So if you are trying to get beta 1, beta 2 will always be there. But beta 3, there is hope to get hold of that, and that is pretty simple. What you do is this: you take, say, the first row, and you take this sixth row, you subtract the sixth row from the first row, and you can get hold of beta 3. So if I take, say, y6 minus y1, that will be an unbiased estimator of beta 3. I am not saying it is the best estimator, but it's a meaningful thing. You can do that. But beta 1 you can't do. Now, if I want to make this precise, here is one way of making it precise. I might say that it is possible to get 2 sets of beta i's, that is beta 1, beta 2, beta 3, 3 values, and 2 sets of such values, for each of which beta 1 plus beta 2 plus beta 3, that is this combination, and beta 1 plus beta 2 plus 2 beta 3 will be the same. Yet, beta 1s are actually different. So it is possible to get that. Because it is possible to get that, so you cannot say I can find beta 1 uniquely. You understand, it is like this. I give you 2 numbers. Say. I have one number A in my left hand and another number B in my right hand. I add them up. I get the answer to be 10, and I ask you to find out A and B individually based on that information. You can't do that. If you cannot do that, even when I give you A and B, A plus B exactly, you have no way of getting A and B if I give you A plus B only approximately. So that is the idea. In this case, if I give you beta 1 plus beta 2 plus beta 3 exactly, no epsilon, So all these y1 to y5 are same, and that is exactly beta 1 plus beta 2 plus beta 3. Similarly, I give you exactly beta 1 plus beta 2 plus twice beta 3. Even then, you have no hope of obtaining beta 1, right? So if you cannot obtain beta 1 even from the precise data, precise information, how on earth can you hope to get it when you have errors epsilon 1 to epsilon 9? You understand the point? So we generally say, that's the term, that beta 1 is not identifiable from this setup. Meaning that you can have multiple values of beta 1 with possible adjustment in the other parameters, which will give rise to the same data. So I can have beta 1 equal to 1 and beta 2 equal to 5, but I could have beta 1 equal to say 2 and adjust beta 2, make it 4. So beta 1 plus beta 2 still remains 6. You cannot say whether 1 comma 5 was the situation or 2 comma 4. Now if I want to express it as a condition, here we understood it intuitively. If I want to understand it as a rigorous mathematical condition, let's look at it in the following way. I had my, what should I call it, the design matrix. So this is my design matrix. And what is my beta 1 after all? Beta 1 and beta 2 are nothing but two linear combinations of beta i's. For beta 1, the linear combination is beta 1 is 1, 0, 0 times this, and beta 3 is 0, 0, 1. Now the point why we could not obtain beta 1 separately was because I could not express beta 1 as a combination of these equations. For example, for beta 3 I could do that. I said I will take this equation, subtract the top equation from the sixth equation, I will get beta 3, which basically means I take this row of x, from it I will subtract that row, and I will end up with 0, 0, 1. In this case, I cannot do that. So it should not come as a great surprise that the condition of identifiability in this case reduces to checking whether this vector belongs to the row space of X.